Okay, so I guess I'm going to finish up our discussion of homotopical categories today. And so I just want to talk about a couple of different ways other than the ones that we talked about yesterday, and then how they all fit together. So I think it was Jesus yesterday that asked the question, okay, so we took these homotopical versions from a couple different approaches of nerves of categories. And so there's this question of, well, could you have a homotopical version of a category to begin with? And so one way to think about that, it goes back to something that we talked about on Tuesday in the very first lecture, and that's that of a simplicial category, or a category enriched in simplicial sets. So let me go back. It's been a few days, and people aren't very awake this morning, so I'll remind you. So a simplicial category. And notice that this terminology can be a little bit ambiguous because it could mean a category enriched in simplicial sets. Now, it mean a category enriched in simplicial sets, and that's what I want it to mean. It could also mean a simplicial object in categories. The first is a special case of the second. That's the one I want to consider. Just sort of a warning, if you see simplicial category in the literature, it could mean either one. So you have to figure out the context, which one it is. Okay, so a simplicial category C is a category enriched in simplicial sets. Okay, so i.e. we have just the objects of C, which is a set, or if this isn't, maybe I'll just say small here, just to, in general, I mean, you could have one that's not small. It could have a class of objects, but in any case, it doesn't have any additional structure. And if you take any two objects, then you have a simplicial set which I'll write as map C X, Y. So I'll generally use hom when I mean hom set and map when I mean hom simplicial set. Okay, so, and again, just to recall from the first lecture is that this is a special case of a simplicial object in cat, basically just where there's no structure on the objects. Yeah?
You also want composition of morphisms to be a simplicial morphism, right?
Yes. Yeah, so you're using the product on simplicial sets to have, say, for your composition, you want, say, map XY cross map YZ to map XZ, so you want this to be a function in the category of simplicial sets. And just a comment, not relevant here, but if you're familiar with this sort of thing, if you could enrich in something where you don't want to consider Cartesian product, but maybe you want to consider some kind of tensor product, and that's fine too. Basically, you just need a sufficiently nice monoidal category in order to do this. So you could do it like DG categories or categories enriched in chain complexes, and then you'd have a tensor product there. Or spectra, then you'd have a smash product. So yeah, everything has to be compatible. I'm not listing everything there. Okay, so then we could say, well, this is a generalization of a category. Can I take the nerve of it? So what we would like now to have some kind of nerve of C, where C is a simplicial category, to be a quasi-category or a complete Siegel space. So there, and since quasi-categories and complete single spaces are, even essentially very different objects, these are simplicial sets, these are bisimplicial sets, we're going to have a couple pretty different constructions in order to make sense of this. And it's not quite going to work. So we're actually going to introduce some other approaches, but there's a lot of interesting stuff can come out of this. So Okay, so I'm going to start with trying to get the nerve of a simplicial category to be a bisimplicial set. Okay, so I'm going to call this the simplicial nerve. So let C be a small simplicial category. Then so its simplicial nerve is defined by, now this gets a little more difficult to define rigorously given what I've presented to you in the lectures, but the idea is I want something like nerve of C at level n should be something like map from n into C. Now, so here this suggests that I should be able to get some kind of mapping object, some kind of mapping simplicial set. Now here C is a simplicial category, n is still just an ordinary category, but you can always think of any ordinary category as a simplicial category that just has a discrete simplicial set of morphisms. So put this in quotes, since I haven't really given you the background to understand where you would actually get a simplicial set like that. Another way to think of it is to just say, well, I'm going to get a bisimplicial set where, so I have the objects of C in degree 0, and then in level, this is a way you could describe the ordinary nerve as a simplicial set. You could have objects, and then you have the morphisms, and then you have the composable morphisms, and then you just have iterated compositions. But now these guys, if C is a simplicial category, then these are simplicial sets. And then you force this one to be thought of as a simplicial set, but it's discrete. It's not interesting in its simplicial structure, just because the objects in the original C didn't have any simplicial structure. Okay, so some properties of this. So nerve of C is a bisimplicial set such that, so two things are true. So we've already mentioned, so the objects of C, this forms, well, which is nerve C level 0 is a discrete simplicial set. And then the second property, which should remind us of things we saw yesterday, is that the nerve of C at level n, if we're really coming from a simplicial category, this will be on the nose isomorphic to this iterated pullback of 1 simplices along 0 simplices. So here's this Siegel condition appearing again in a strict form. Okay. So even though we're saying this, we're thinking of this as something homotopical, a homotopical version of a category, it still has some strictness to it. In particular, I mean, this composition is strict. We've got strict associativity, we've got identities, we've got all kinds of stuff that's still fairly strict, even though we're being homotopical in the sense that we have a whole space of morphisms, and they're not just forming a set. Okay? So, but we could look at this in the same way that we looked at things yesterday and say, well, I could weaken this. You know, I'm a homotopy theorist. I don't want things being isomorphisms of simplicial sets. I want them to be weak homotopy equivalences. So this could lead us to another definition. Now, there's going to be two parts to this, and one we saw yesterday, and that's just something being a Siegel space. Maybe I didn't say that exactly, but something that satisfies the first two conditions of being a complete Siegel space. So a bisimplicial set W is a Siegel space if two conditions hold. Again, the first is technical, just W is injective fibrant. That's just there to make some of the constructions nice and homotopy invariant. And then the second condition is that Wn is weakly equivalent to this iterated pullback. So it looks like we have some kind of weak composition. So, and then we had this extra condition if we wanted this to be complete. So something to notice is that if we take the simplicial nerve of a simplicial category, well, okay, maybe this guy isn't obvious, but it certainly satisfies this. It satisfies a strict version of this. So notice that, and I guess, I mean, I'd have to think about this. You may need to have some, I'm trying to think. You may need to have like these mapping spaces being fibrant simplicial sets in order for this to be strictly true. Let me shove that under the rug. I want it in the definition just so you know it needs to be there, but when I'm saying that this is a Siegel space, I may be shoving it under the rug a little bit. Okay, so notice that nerve of C is a Siegel space, but it's almost never a complete Siegel space. There's just not enough stuff in this discrete degree 0 set to really have any hope of being complete. Question?
Yeah, I may have simply forgotten, but did we put like an injective and projective model structure on bisimplicial sets or only on simplicial sets?
No, the injective and projective was on bisimplicial sets. We didn't put it on simplicial sets.
Okay.
The idea is that you wanted a model structure on bisimplicial sets where your weak equivalences were level-wise weak equivalences simplicial sets.
Okay.
And then you chose whether you wanted the fibrations or the cofibrations to be level-wise. So this was the one where the cofibrations were level-wise.
Okay.
Okay, so this says that this simplicial nerve construction does give us some kind of notion of, nerve of a simplicial category, but it's not going to give us maybe what we were hoping for, which was, this homotopical category gives an example of this kind of homotopical category. It's actually going to introduce yet another one. Okay, so definition. So a bisimplicial set X is this is a terrible name, but this is what it is a Siegel pre-category. if x0 is discrete. So far, that's the only condition. I just don't want to have an honest simplicial set here. I just want something that really looks like a set disguised as a simplicial set. And then I want to impose a Siegel condition. So we'll say it is a Siegel category if also we have the Siegel condition. I guess I haven't been putting the ends here, but okay. Yeah, okay, I guess it's down here. That's where the other one could have gone. Okay. Okay. So now we have this dilemma in that it said, all right, we had these notions of homotopical versions of nerves of categories. And then we went back and we said, okay, here's our notion of homotopical category, which is a simplicial category. But we still ended up with something kind of strict, and we're weakening the conditions on the nerve of it, and we get another definition. We say, well, gosh, maybe simplicial categories weren't homotopical enough. Maybe they're too rigid. Do we have degrees of how homotopical we are? Because this certainly looks like a weaker condition than this. Okay, so we want to have some kind of way to compare them. Okay, so let me just write down partly what I said. So the nerve of a simplicial category, so there's a strict version of this. All right, well, in order to do any kind of comparison here, we need to know what we mean by equivalence of them. So let's start with what are equivalences of simplicial categories. Here, of course, we're setting up to have a model category structure on simplicial categories and on Siegel categories. Okay, so let's start with simplicial categories. So a quick comment before I get to the definition. So notice you can always get an ordinary category from a simplicial category by just applying pi0 to all the mapping spaces. If you're more comfortable, take the geometric realization and then take pi0. So you just take components of these mapping spaces, and that's going to give you an ordinary category. We're going to call that pi0 of C. So we have the objects are exactly the same. So objects of pi0 of C are the objects of C. And our Hom set is just an ordinary category. So Hom pi0 C between two objects is defined to be pi0 of the mapping space in C. You can check that works and actually does give a category. Okay, so now we're ready for our definition of equivalence. So a simplicial functor, which is, by the way, exactly what you think it should be. You send objects to objects and then mapping spaces to mapping spaces in a, in the way that you think they should. go. So a simplicial functor, f from C to D, is a Dwyer-Kohn equivalence if two things are true. Now this should really remind you of our definition of equivalence of categories, but it's going to look more homotopical. So if I take any two objects in C, well, now I want to look at what happens if I take the mapping object between x and y and send it over to D. And now I'm just going to require that to be a weak equivalence of simplicial sets. And then our second condition is the same, is that f needs to be f is essentially surjective, but what does that mean? I haven't told you what that means. So you can say that pi 0 of f from pi 0 of C to pi 0 of D is essentially surjective. In fact, you really have that this is an equivalence of categories, but if this is a weak equivalence of simplicial sets, then when you pass to the Hom sets in pi 0, they're going to be forced to be isomorphisms. So you have, in fact, that this functor is an equivalence of categories, but part of that's already built in. So we can just say that it's essentially surjective. Okay. Okay.
Of using pi 0 of f instead of just f as being essentially surjective is because things could become isomorphisms or whatever that aren't already.
Yeah, it's just, you could say it that way, but then you have to say what you mean by essentially surjective. Yeah, but you could have something that's only, you could have things sort of essentially, you could have things up to homotopy. Okay. Now, you could have something that becomes an isomorphism here, but that wasn't an isomorphism in the original simplicial category. So you need to be a little careful with that. Okay. Yes.
This might derail you more than you want to, so that's fine. But could you draw two categories that are like Dwyer-Kohn equivalent, just with some small?
Sure. So here's our favorite category C from yesterday. It's a very boring one, but it's trivially a simplicial category. And you could include that into something like this, where maybe you have two objects, and you have a whole simplicial set of morphisms between all of them, but they're all contractible. So maybe this is D with all and they don't. Because if these are all contractible, when you apply pi 0, then they're all just going to become a single morphism. And then because you have pi 0 of D is just back to this guy. But then, if you're including this object into here, and you're comparing, well, this is just the identity, and then this is some bigger space, but it's contractible, so this is going to be a weak equivalence. These are actually important because these are some of our acyclic cofibrations in what I'm going to say we're about to have a model structure, but I'm not going to, they're some of the generating acyclic cofibrations, if you know what that means, but I haven't talked about cofibrillary generated model categories, but yeah. Okay. Okay, so then the theorem is that these actually are the weak equivalences in a model structure. So I'm going to start giving these names. Let me just call this SC for simplicial category on the category of small simplicial categories in which no, I don't want to talk about the fibrant objects. Which the weak equivalences are the Dwyer-Kahn equivalences. Okay, so and just a comment here that just because I think this hasn't really come up yet in most of the model structures we've seen so far, kind of everything's fibrant or everything's cofibrant, and this is one where neither of those is true. The cofibrations are inclusions, but not all inclusions are cofibrations. And then the fibrant objects have some kind of lifting of isomorphism type property. Upshot is the fibrant objects here are the simplicial categories whose mapping spaces are all Kahn complexes, which hopefully seems like a sensible thing for them to be. Okay, so what we would really like to do then is to compare this model structure to the ones that we talked about yesterday. But at the moment, I actually want to start comparing it to this notion of Siegel category, because that's going to make use of this nerve functor. We have this nice functor from here to Siegel categories, and so we'd like to investigate that. For that, I need a little bit of terminology because I want to make any kind of comparison believable. I better tell you what the weak equivalences are between Siegel categories. Now, remember yesterday our model structures it was not a model category on the category of quasi-categories. We needed to have something bigger. We had a model structure on simplicial sets where the fibrant objects were quasi-categories. We had a model structure on bisimplicial sets where the fibrant objects were complete Siegel spaces. This is due to just that very first axiom for model categories. If you just take complete Siegel spaces, those properties are not going to be retained under passing to limits and co-limits, things like this. So we need to work in a bigger category. Simplicial categories are kind of nice. They're strict enough that we don't have that problem. But we're going to have that problem with Siegel categories. And that's actually why I've introduced Siegel precategories. We're going to have a model structure on the category of Siegel precategories where the fibrant objects are Siegel categories. Okay, but that's going to make things a little more complicated saying what the weak equivalences are. So we need some terminology. We can just do this in the setting of Siegel spaces. And what this terminology is doing is saying, I look at a Siegel space and I see something that's starting to behave like a category. Not strictly, but I've got sort of W0, it's looking like objects. I have W1 that looks like morphisms. I have these Siegel conditions that looks like I can compose things. So I want to introduce some terminology so that we can kind of put that on a little firmer footing. Now, in a Siegel space, in general, this W0, this thing we want to think of as objects, well, it's a space. It's a simplicial set. So I only really want to think about, I'm keeping simplicial categories in mind, I really only want a set of objects. So let's just take the zero simplices of that. So let's let objects of W be defined to be W0, 0, the zero simplices of W0. So we have a set. Now I want to define mapping spaces. So I'm going to do that by saying, well, I have W1. I have these two face maps going down to W0, and I want to say, well, if I pick my favorite pair of objects in here, I want to take the pullback, or this is just the homotopy fiber of this map. Okay, I claim it's a homotopy fiber. This injective fibrant business tells me this is going to be a fibration, and so it's actually a homotopy fiber. So if you don't know what I'm talking about there, don't worry about it. It's just making sure things are well behaved. So I just take a pullback here. This is going to be the mapping space. Okay. And then our Siegel condition. Now there's a little more work to make this fully rigorous. This was all done by Charles Rask. So, but the Siegel condition gives a weak composition of these mapping spaces. Okay, well, what else do we need for a category? We've got objects, we've got morphisms, we've got composition, we need identities. But we can do that too just by saying, let's just apply the degeneracy operator to W0, and whatever the image of that is, that should be the identity maps. So S0 of W0, or W00 if you want to be really fussy. This is the space of identity maps. Okay, so that says we have enough to have something that is behaving kind of like a simplicial category. But we actually have something else, because these are mapping spaces and not just Hom sets. And that's that if we have a notion of identity map, and if we have a notion of composition, we have a notion of homotopy equivalence. Say, well, if I have something in my mapping space and I have something going back the other way, and if I compose them and I get something that's homotopic, which makes sense, these are spaces, homotopic to an identity, then we say that it's a homotopy equivalence. So a homotopy equivalence in W1 has an up to homotopy inverse and you can show, so this is all rigorously in this paper of Charles Rask, where he introduces Siegel spaces and complete Siegel spaces, that this is preserved by components. So if you're in the, if you say like, a zero simplex of some component of a mapping space is a homotopy equivalence, the whole component can be regarded as being all homotopy equivalences. So this gives us a pretty nice, get a subspace, called WHEQ for homotopy equivalence sitting inside of W1. And then we can also use this to get a homotopy category which I'll write as we write it for model categories. Okay, so notice we really need to have, so we can do this, but we really need some kind of Siegel condition. If we had an arbitrary bisimplicial set, then, certainly we could define objects and we could define these, but they're not going to have any nice properties. You're not going to have any composition or, so we really need to have this Siegel condition. Even though it's a weak Siegel condition, we need for this to work.
Do you have any kind of associativity up to homotopy too?
Yeah, and so that's part of what I mean by weak composition. So it's partly you have composition, but it's not necessarily unique, but then it is up to homotopy associative as well. Yeah. Okay, so kind of an intermediate to a theorem I gave yesterday, so due to Rask, is that there is a model structure on the category of bisimplicial sets in which the fibrant objects are Siegel spaces. Okay. So what does that do for us? Well, that says that up to weak equivalence in this model category, I can replace any bisimplicial set with a Siegel space. Okay? So I have some kind of fibrant replacement functor, some way that I can replace any bisimplicial set with a Siegel space. Okay, so I want to use that in the context of Siegel precategories. I want to be able to say, okay, if I have a Siegel precategory, I can turn it into a Siegel category. If I just use fibrant replacement here, I can possibly run into trouble because nothing guarantees here that if I have this discreteness condition, it's going to be preserved by the fibrant replacement functor. So a technical fact here is you can tweak the fibrant replacement functor here so that you preserve this discreteness property. So that if I start with a Siegel precategory, I can do some kind of replacement of it and get a Siegel category. But it's using this, but then tweaking it a little bit.
How thickly does Siegel precategories fit inside bisimplicial sets? Are there a lot of them, or are there not that many?
Well, there's certainly a lot more that aren't because you've got a lot of choices for what X0 could be.
But it's not full, for instance, not full subcategory?
No, it should be a full subcategory because, if you're mapping something with discrete objects to discrete objects, then, you're not going to get something else if you have to, So yeah, it's full and it's complete and co-complete.
Okay.
You've got the limits and co-limits, so it's pretty nice. Okay, so this is just our technical proposition here. Let X be a Siegel precategory. Then there exists a Siegel category, which I'll write as Lx. It's some kind of localization, which is weakly equivalent to X in the Siegel space model structure. Now what I'm really going to want is this is going to be like some kind of fibrant replacement functor in some model category. The problem is I actually need this to get the model category. So, don't always have everything that you want. And the other nice fact here is it doesn't change that object set. Or what's in degree 0. So x0 is going to be exactly equal to Lx0. So I can do this Siegel space replacement without messing with what's in degree 0 whatsoever. Okay, this, it turns out, is going to be, this is enough for me to define something like Dwyer-Kahn equivalences. In fact, they're enough like Dwyer-Kahn equivalences. We're still going to call them Dwyer-Kahn equivalences between Siegel precategories. Okay. So a map F from X to Y of Siegel precategories is a Dwyer-Kahn equivalence if, and now we just have to, this is going to look very similar but we have to be careful about when things are defined and make sense. So first of all, for every x and y in x0, we have, well, we want to look at these mapping spaces, but x is just a Siegel precategory. So let me apply this Siegelification functor. So I'm just going to look at mapping spaces in Lx. Since my objects don't change, that's fine. And compare this to the mapping space in Ly between f of x and f of y. And I'm going to want all of those to be weak equivalences of simplicial sets. And then secondly, I'm going to use this homotopy category. And so I want, again, I need to use Lx and Ly. So I want this functor between these homotopy categories to be essentially surjective. Okay.
Could you say a little more about how Alex is like a localization?
Yeah, so something I didn't talk about all, there's notion of a localization of model categories.
It's like a
It's a Bausfield localization of model categories. So that's how this model structure comes from. So you start with the injective model structure on bisimplicial sets, and you localize it. You put in some new weak equivalences that will then force the fibrant objects to be Siegel spaces. So in this context, it's a localization in the sense that, well, in a localized model structure, localization and fibrant replacement are the same thing. So technically, this guy isn't a localization because, so this, I don't want to say too much about this. This discreteness condition is really problematic in that you no longer, so that, I mean, here's a nice exercise if you want one, is that if you just look at, if you take all bisimplicial sets, you have these level-wise model structures. If you restrict to Siegel precategories, you cannot have a level-wise model structure on them. You can check that it's impossible to get some of the factorizations that you need. So it's just impossible. So what we, in an ideal world, what we'd like to do is say, well, take Siegel precategories, do some kind of localization, just like what happens here. We get the fibrant objects being some kind of Siegel categories. It doesn't work. You have to do it manually. And it's really hard. But this is, this is how you do it. You use this model structure and you tweak things as necessary to get this sort of Siegel category replacement. Okay, before I state the next theorem, let me just comment that in the there are reasons why in this model structure, our definition of Siegel spaces and complete Siegel spaces, that we wanted things to be injective fibrant. There's reasons for that, but you could also define the analog of Siegel spaces, complete Siegel spaces, where you instead use the projective model structure. Turns out for the things we want to do, it's not so useful. But for Siegel categories, we actually want to use both. Something that's again, we're not tweaking an injective or projective model structure because they don't exist here. But we want something that behaves like one would. Okay, be able to say why that is, why we need both a little bit later. Okay, so a theorem. So one of these was originally due to Pellissier, and I gave another proof, and then the second model structure is mine. So there are two model structures. On the category of Siegel precategories. Such that So in each of them, the weak equivalences are going to be the same. They're just going to be the Dwyer-Kahn equivalences. Okay. Let me just make a comment about the distinction between them. So I'll write them as CCAT sub C and sub F. Capital S, capital C, don't get them confused with Jesus's sectional category. So CCAT sub C is going to have, so the sub C is suggesting this has some properties like an injective model structure. So it has all objects cofibrant, which is nice. And then the fibrant objects, in fact, your cofibrations are all inclusions. But then the fibrant objects are the injective fibrant. So injective fibrant in the injective model structure on bisimplicial sets, Siegel categories. Notice, unlike Siegel spaces and complete Siegel spaces, I didn't impose a fibrancy condition on Siegel categories. The reason is I need both kinds. So the other guy, it's much harder, so CCAT sub F, it's much harder to say anything about the cofibrations or the fibrations. I'll just say that not all inclusions are cofibrations here, but I'll just say that it has fibrant objects. The projective fibrant Siegel categories. Okay. Okay, but then I guess I'll just say, I'll include it in this theorem. A third property is that the identity functor gives equivalent equivalence between the two. Again, it matters which one's the left adjoint. So remember I said this one had fewer cofibrations than this guy, so we want this identity to be the left adjoint, so everything that's a cofibration here will still be a cofibration there. So this is a equivalent equivalence. Okay. Okay, now finally, we can look at how does this model structure compare to simplicial categories. How do Siegel categories that look strictly weaker than simplicial categories, how do they compare? Okay, and so the simplicial nerve functor that we talked about at the beginning of the talk. So nerve, so I can think of this functor as going from simplicial categories to well, this is Siegel the category of Siegel pre-categories. Has a left adjoint. So you can think of that as some kind of rigidification functor. I could take any Siegel pre-category here and I can send it to a Siegel category. But in particular, if it was a Siegel category, so it has this weak composition, this left adjoint is going to turn it into something which is strictly a simplicial category. So I call this a rigidification functor. You don't want to actually describe what this functor does. It just exists for formal reasons, but would be really ugly to write down. And then this adjoint pair defines equivalent equivalence. Now, this should surprise you at least a little bit, because it sure looked like a Siegel category was strictly weaker than a simplicial category. The nerve of a simplicial category had this much stricter Siegel condition. Things were isomorphisms instead of weak equivalences. What this theorem says is that the difference, though, that weakening doesn't, from a homotopical point of view, it doesn't make a difference. That if I take something weak, I make it strict, I send it back over here, I get something strict, but it's weakly equivalent, it's Dwyer-Kahn equivalent to the thing that I started with. Okay. I mean, a comment on why this is nice is just, I mean, simplicial categories are very useful. They appear in lots of places in math, but you also have things arising in examples that are weaker, that are Siegel categories. But here you say, well, it's okay. They're encoding the same information. Okay, so that's the upshot of that. But okay, way back at the beginning of the talk, our goal was, though, to compare simplicial categories to complete Siegel spaces. Well, we can do that. So I should say, I forgot one point here, that I have to specify which model structure. This is part of the importance here, that this is a Quillen equivalence, but only if I use this projective-like model structure. And the reason is that, you know, this model structure looks a bit more like the simplicial category model structure. You know, not everything is cofibrant. The fibrin objects have some similarities. So we really need this model structure. Okay, but now I want to compare Siegel categories to complete Siegel spaces. And I can do that starting off with just the inclusion functor. From Siegel precategories to bisimplicial sets. Just take all the guys that have this restriction in degree 0, include it into the category of all of them. Okay. And so this is the underlying category for Siegel categories. This is the underlying category for complete Siegel spaces. And then we can prove that this induces a Quillen equivalence. So the inclusion functor, so I'll just say this inclusion functor has a right adjoint. And we can think of this as a discretization functor. We're taking something that has no assumptions in degree 0 and forcing degree 0 to be discrete. And then this induces a Quillen equivalence. But here, I need to use the other model structure. So I need to use the injective-like model structure. I'll use CSS for the complete Siegel space model structure. Okay. So hopefully now you can see why we needed both model structures, because here we could compare this guy to simplicial categories, we could compare this guy to complete Siegel spaces, and if you follow the chain of Quillen equivalences, they don't compose. We have left adjoints going in different directions. So it's not like we just weren't smart enough to see what the functor was from one to the other. They actually just don't compose into a single one, at least not using these methods. Okay, I mean, maybe I'll just go ahead and write that down. So the chain, So we have here simplicial categories, 2 Siegel categories with the projective-like model structure. Then we have Siegel categories with the injective-like model structure. And then we have the complete Siegel space model structure. And then last time we mentioned that we have equivalence here with the quasi-category model structure. Now, this guy is weird, and I didn't, in that you could pick which direction you want to go. So we actually have 2 different equivalences, one in each direction. Meaning one of them, the left adjoint's going here, one where the left adjoint's going the other way. Okay, so that right there is enough to say these are all equivalent. These ways of thinking about homotopical categories are they're all encoding the same information, but in different form. However, there is also a way to get directly from simplicial categories to quasi-categories. So let me just say a little bit about that. Let C be a simplicial category. So its coherent nerve which I'll write as n tilde of C, is the simplicial set defined by so it's n simplices, so NCN is going to be equal to, now this should be a set now. Now my ordinary nerve, I would just take hom from N into C, but this isn't going to be enough because this is just some discrete guy. I'm not going to pick up all the simplicial information in C if I just use this. So what I'm going to do is take F star of N. This is the free simplicial category generated by the category N. Now here we're using the simplicial object in categories. So you say, okay, forget that N was a category. Just think of it, forget that it has composition, just think of it as a directed graph. Take the free category on that. That gives you something. Then forget again and take the free category on that. Forget again, take the free category on that. The process of taking these free categories has a simplicial structure. You can get face and degeneracy maps, but we're not messing with the objects at all. So it's going to be a simplicial category in the sense we care about. And so this is enough. Now you just look at Hom sets from this into C. Okay, so then a theorem that was proved by several different people. I think the first proof was due to Joyal. There's a proof due to Lurie. And then Duggar and Spivak gave another proof. And that's that the coherent nerve functor has a left adjoint which defines a equivalence from simplicial categories to quasi-categories. Okay. Yeah.
Is there some like nice subcategory, simplicial categories where full equivalences from all categories or full equivalences, so you can just identify all those things as one object?
Okay. Can you say that you want a subcategory
Like,
that?
can you put some kind of model structure on model categories? So equivalences.
No. I mean, not that we know of. And there's people always like to come back and ask this question, and I don't know. It seems to be too rigid to get a model structure. I know there's still people that think about that. I don't know. Let me come back to that perspective a little bit in a minute. I have a little bit of time. So are there any questions here? I should add that there's also, anyway, so this gives us something going the other way, I guess, here and back. There's also, you actually get two quivalent equivalences also from Siegel categories to quasi-categories. They're essentially the same functors as they're used for complete Siegel spaces. So there's actually another sort of pair going from there to there that's also due to Joyal and Tierney. So we have even more equivalent equivalences than we need. Okay, so in my last 10 minutes or so, I want to talk about, I kind of took one approach here in these talks, which was, let's start with like the nerve of a category, and then let's try to weaken it. Let's try to get something that looks like a category, but has a little more flexibility. But these structures actually all arose from some other perspectives, and I just want to say a little bit about what those perspectives are, and one of them is going to kind of feed into your question, and also present another model here we haven't talked about. So going back to Wednesday's talk, we talked about model categories, and so the basic data of a model category was that you have, a category and you have some weak equivalences that you want to invert. Now, then you put in all this other structure so you can get a nice homotopy category and all these things. But you can certainly imagine that sometimes you have a category and you've got weak equivalences and you don't have a model category. But you could say that the basic data of what you mean by a homotopy theory is still there. So this is really coming from this question of what is a homotopy theory. So you could say, this is a very loose definition, but say a homotopy theory is simply a category with weak equivalences. Okay. And then if you have the structure of a model category, on that category with weak equivalences, you have a lot more power. You can compute homotopy limits and co-limits, and you can do all these things, and life is really good. But sometimes you simply don't have that information. But some work of Dwyer and Kahn in the 80s, and this was the work that led to the notion of equivalence that now has their name attached to it. And they said they have a couple different methods for what's called simplicial localization. And their input was a category with weak equivalences, and then the output is a simplicial category. And I, of course, don't have time to say anything about what these methods are, but the remarkable thing that they also proved is that up to Dwyer-Kahn equivalence, every simplicial category arises in this way. Which is maybe a bit surprising. Now, this construction is much nicer if this is actually a model category. But this sort of converse is definitely not going to be true. Nothing here said that this category had to be complete and co-complete. If it doesn't have limits and co-limits, we have no hope of having a model structure. So model categories definitely form a proper subclass of these guys. But what this suggests is that, sort of a slogan is that simplicial, I'll put the quote somewhere else, simplicial categories sort of are homotopy theories. They encode the same basic information of them. And so this question of, let's now look at the homotopy theory of simplicial categories, let's look at their weak equivalences, then that's like the homotopy theory of homotopy theories. So you're doing like meta homotopy theory, I don't know. And this is what, if you look at Charles Rusk's paper where he introduced complete Siegel spaces, it was an attempt to find another model other than simplicial category. For this, his paper is called A Model for the Homotopy Theory of Homotopy Theory. And this was actually recently revisited by Barwick and Kahn, who said, well, what about categories with weak equivalences? Could we put a model structure on them? And they actually did, and then showed that it was equivalent, I think, to the complete Siegel space model structure. They call them relative categories, but it's this same thing as a category with weak equivalences. So that's yet another way to think about this. And that's actually the viewpoint where I got into this, and how I got interested in it was thinking of all these as ways to think about homotopy theories. Now, to go back to your question about model categories, one thing this is nice for, because this seems to be sort of well, we don't seem to have a model category on model categories, but this is kind of the next best thing. For example, there's some definitions out there of what is a homotopy pullback of model categories. Well, there's a definition, but how do we know it's the right thing? To say what a homotopy limit is, you need a model structure in order to verify that the homotopy limit is really the right thing. But what you can do is say, let me start with my model category, let me hit it with, well, you can hit it with simplicial localization. Turns out, hit it with a functor that goes all the way to complete Siegel spaces. And you could really just do this whole, hit it with simplicial localization and go along here. And then say, okay, well, if I take this homotopy pullback construction of model categories and send it over, or if I send the diagram over and look at the homotopy pullback here, where I have a well-defined notion of homotopy limit, are they the same? And the answer is yes. So it says, oh, okay, this gives me a way to verify that that definition makes sense, even if I don't have a model category of model categories to tell me what a homotopy pullback should be. But like I said, people are still trying to think about this issue. Is there a model structure on model categories? And but it's not known. Okay. Okay. So that's another perspective. Another perspective is out of higher categories. So I don't have a lot of time, but let me just say a little bit about this because it's also significant. So what do we mean by a higher category? So a strict or weak N category, well, this is going to have objects, and it's going to have morphisms. I'm now going to call those one morphisms. And then it's going to have two morphisms, which go between one morphisms. And so forth up until you get to N morphisms. So the kind of pictures you should be thinking, you can't draw this for very high values of N, but okay, you have morphisms between your objects. then you have a two morphism that goes from a morphism to another. You could imagine if you have two morphisms, you could have a three morphism between them, and so on and so forth. And these can be strict, in which case there's no problem, or they can be weak, where they're only associative up to isomorphism, and then you have coherence laws. If any of you have worked with monoidal categories, you know where this kind of stuff arises. So it's a very hard problem. There's lots of definitions about what weekend categories should be, but we can't really compare them. In which model for n+1 categories do you compare them? So it's very difficult. You can also say, well, if you have n morphisms for all n, then you get what you could call an infinity category. So you just don't stop at any point. You just keep having morphisms between morphisms between morphisms. Okay, that sounds like you've just made the problem even more complicated. But what all these things we've been talking about are what are called infinity one categories. So an infinity one category has all n morphisms, weakly maybe, invertible, for every n greater than 1. And it turns out that this notion of infinity one category, it essentially is the same information as a homotopy theory, which is the same information as a homotopical category. They're all different perspectives or motivations for these same objects. And the funny thing is that you would think that in infinity one category, you go all the way out to infinity, and then you put some more conditions on it, you would think that'd be much more complicated than a weekend category. But the fact is that it's not. We've seen that we have all these different models and we can compare them, which is something that still seems really intractable back over here. So anyway, it's kind of a crash course. Often, especially in Jacob Lurie's work and lots of other people, they use infinity category and they mean what I've called an infinity one category here. So just to avoid confusion, if you see that, it often doesn't mean this. It means this. But okay, I'll stop there.